issue which could be that for some users you have 100 preferences, for others you have 4, because all these people that go in the internet sometimes they are occasional.
That's what I want. A couple per user.
So let's ignore all these issues. Let's assume that for each person we have 10, 20, 30 preferences, but there are several thousand movies. The question is this enough information to estimate the underlying low rank model? This question has been answered, and the way it is estimated is by solving this problem. And like in the case of the lasso, you need to show that the solution of this problem is close to the underlying model. Right? So you need to work hard for that. We don't discuss this. But the solution of this problem will be low rank with yes. Okay. Because you have the soft thresholding operator applied to the singular value, so if the singular values are small, then the solution will put them to 0. So the same principle that were used in the case of the lasso apply here. So by using this, it's called this trace norm, nuclear norm regularization, you favor low rank matrices. And therefore you hope that if the underlying model is low rank, these will estimate it better, right? For example, using the Frobenius norm, the ridge regression, right? To understand these lectures, I would say this should be the last rank first. So first, work out the lasso, and then understand why the solution is what it is in the simple case. Have an idea that it encourages sparsity. Then if you want to know more, there are some references at the end which tells you more quantitatively why it works in a statistical sense. Then, well, maybe you want to digest, if you like, some of this convex analysis stuff, which I just touched upon. So, what are the conditions for optimality, because we will use them next week. Then understand the structure sparsity, group lasso, multitask. Last one is this one. I would say is the most sophisticated. Mostly perhaps sophisticated because it involves singular values, which are complicated objects, in my view. So, if this is not clear, the first time I heard this stuff was 2 to 10 years ago, which was 5 years ago. No, I'm not exaggerating. I think it was, so it was unclear to everybody. In research, you know the tools. If you work in research, you know these tools, but how to fit them into a problem is not so easy. So you are students, you have the additional difficulty that some of the tools you don't know. So if something's not clear, no panic. Take it easy, go to the book, and so if you want to use this stuff in some real problems that you are working on, some of you are PhD students, you need to work out a little more the details. And also, if you come more from a practical, sorry for the digression, if you come more from a practical angle, you also need to understand how to use your hands, so how to make your hands dirty. So there are some implementations in the internet. They don't work. If you have a big matrix, they never. So press the button and you never converge. So there are also important issues, important optimization issues. So another nice thing about this stuff is that it developed recently, and it merges ideas from statistics, so the sparsity assumption, and these results, which I didn't describe. So, do I estimate the underlying model? It merges idea from statistics with idea from optimization. How do I solve the problem, right? And it is difficult to master both these two different areas, right? Because very different tools are put together. So, but then the point is that to have a first grasp of these ideas, you need to maybe understand a bit more intuitively, right? What is the rationale, right, behind doing this, right? The rationale is that is the main rationale behind regularization. Under some condition, the solution becomes unique. and the solution favors, the regularizer favors certain solution over others, and you want to understand how that is done, right? So, in the very special case of the lasso, you see that line by line. So, that's the first step on the ladder. But another point that these stuff are applied widely. So, for example, they are also applied in a supervised learning. This is another. So in a way, it's like 20 years ago, kernel methods started to develop in machine learning. They were already known in statistics for several years, but in machine learning, they found how do you say? I think they developed much more. Because of applications, because of many researchers work on that. One of the first books, by the way, you know, is from John Taylor, who's the head of the department. So 20 years ago, a lot of research activity on kernel methods. And they implement very different assumptions from what we described today. So they are the assumption that they are non-parametric models, so the function is non-linear, and it is smooth, so it goes smoothly for the data. So there is this large margin. So here we discuss a very different assumption. The underlying model has many parameters, but many are zero. So it's a very different. These methods implement very different principles. And these methods develop in the past 10 years, or maybe less, a lot of activity on this method. So maybe it is a new fashion, let's say. So kernel methods, 20 years ago, maybe the SVM is introduced, then people apply to this problem, like it's called this kernel PCA, and then they apply to this. So there is this word to kernelize. So you take any linear problem and you put a kernel, it works. And here is the same. You take any problems and you add some sparsity constraints, and you show that you solve it and it works better. So it's a bit of, so this is the popular science aspect of research. So, but there are interesting problems. So, another one which I want to describe is this one. So, it's also been applied in unsupervised learning, right? So, in a supervised learning, for example, an important problem, what is it? Is estimating the parameter of a Gaussian distribution, right? So it's very different from linear regression or from multitask learning. But it turns out that you can use this sparsity principle in a very natural way also there. So this is the last example which I want to describe. So this is very interesting. And so here we go a bit more back to some probability. Probabilistic modeling. So all these methods can also be derived from maximum posteriori, right? So assuming some models. So here I assume that my data are generated IAD inputs from some density function B.
Should be some in the second product now.
Sorry? Some,
Yes.
Two products, the second might be some.
We'll get there. So I assume that P of X is a Gaussian, right? So I make a parametric model. Data are IAD. They are Gaussian with a mean and a covariance, right? And then you know that the standard way to estimate the parameter is by maximum likelihood. So say one natural way, right? So, you compute the likelihood and you maximize it, or you minimize the minus log likelihoods. Okay. And then if you do the computations, right, you see that the covariance, right, that the maximum likely solution for the covariance is empirical covariance, right? Which is this matrix, right? This is the empirical covariance. Right? And this you see by putting the likelihood, which is the product of the P of xi, right? So you need to maximize over all matrices sigma which are positive definite. Make the underlying covariance must be positive definite. This is the assumption because here you have inverted it. And then you do you work it out. Right, then it's the same as maximizing the sum. You are absolutely right. The sum, right? Because I take the log, the product, right? Because if you want to maximize a function, it's the same as maximizing the log of the function. Right? Taking the log of this. Argmax means the variable which maximizes it. And then you do some computations, which are left as an exercise, but basically you plug this formula here, and you use the fact that this thing can be written as the Frobenius inner product between sigma minus 1 and the rank 1 matrix is 1. It's need to remember this notation, which is very pleasant, but once you are comfortable, it becomes mechanical to use it. And then you get this expression. So I skip the details because we are a bit late. You get this expression. When you see it, you need to maximize over your covariance and you minus the log determinant due to this. And then you have the inner product between the empirical covariance and sigma minus 1. Right? And then here, also we skip some of the details. But so in this case, this function is differentiable at the gradient equal to 0. It gives you that sigma hat is equal to empirical covariance. Well, I skip the details. So if you're interested, you need to work out. This is like an unsupervised learning slide. So a lot of details need to be worked out by the students. Okay. So these are the last lectures of supervised learning. So I move more. So it's very interesting, but we don't have the time to go through all the details. But I think a hint that if you assume that the matrices involved are diagonal, then everything works out beautifully. You can take the derivatives at equal to 0, and that's the way you could prove this. Now, what is interesting is that, so this is maximum likelihood, and you have your data, you find, so here I assume that the mean is known. For example, it could be 0. I'm just interested in finding the covariance, right? And why is it called sparse inverse covariance? Because I assume that, I assume additional constraints on the model, which is that the inverse covariance is sparse. Right? And this has an important meaning, because we know that from the Gaussian distributions, two variables are conditionally independent, right? So which means that P of xi and xj, given the remaining, we call it x rest remaining, is equal to the product, right? So the following result is true. The variables are conditionally independent if and only if sigma minus 1 element ij is equal to 0. This is a fact from Gaussian integration. The beauty of working with the Gaussian distribution. So therefore, if we think that many variables are conditionally independent, we should try to do a penalized maximum likelihood. So in other words, we take a prior, right, which says that we like matrices sigma such that the inverse is sparse. Right? So what we do is this. So we choose our priors, then we compute the posterior, we take the minus log and we minimize it. And at the end, Actually, this is not exactly as I've done it. Actually, let's forget for the moment the penalized maximum likelihood. We just take our likelihood function and instead of minimizing it over sigma more than 0, so first we minimize over sigma minus 1, because it doesn't matter if you minimize over sigma or over sigma minus 1. So if you have f of x, you can minimize over x or over 1 over x, doesn't matter. Right? Because you still explore the space of possible values, right? So instead of minimizing my objective function, let's call it, let's give it a name, f sigma, right? Argmin is equal to argmin of g of w for 0, and w is sigma minus 1, right? And g of w is f of w minus 1. This is a very complicated way to say that I just it's a very complicated way to say that my objective function, which was minus the log determinant of sigma, and then it was minus s sigma minus 1. Okay? I make a change of variable, so sigma is equal to w minus 1, or w is equal to sigma minus 1. And then you use the fact that the determinant of the inverse is minus the determinant of, is it?
1 over.
Say something. There is something.
The inverse, so minus log is.
Yes, yes. So, assign. So the determinant of sigma is minus the determinant of w and vice versa. Then you get this minus sign. So the problem is equivalent to this. But now I introduce my additional constraint. Right? So the constraint is that the inverse covariance, which is w, is sparse. So the novelty, well, at the end is this one. So I would like that the cardinality of this set, so only few components of w are different from 0, and then I relax this constraint, right, by the L1 norm. So the L1 norm can also be seen as a complex approximation of these combinatorial constraints. Right? Something that I didn't mention before. This is very important, right? So if we go back to the lasso, where we minimize, and again, put it here, we will put it here. If you use the cardinality of W, right? Let's read that, okay. So this means that at most k components of W are different from 0. So a way to relax this problem, so this is a combinatorial problem, very difficult to solve. Then you consider this problem, right? Less or equal k. So these two problems are equivalent in some conditions, and the same I do here. I take the L1 norm of the matrix elements. Okay. So this is the problem that I want to study. So this, or perhaps this constraint using the Lagrange multiplier, I put it in the objective function, so it becomes regularized. Right? So this is the problem which is just been studied, and so and similarly, the lasso you can show that this works better, right? If the underlying parameters satisfy the assumption. Okay. So you can show that even if the matrix is W is n times is d times d, right? So say d with dimension. So we need to have at least this square, order of this square sample size to compute all the parameters, right? So if you just count the parameters, but you can show that if many of them are 0, you can find these values with smaller sample size by solving this problem. How we solve this problem is more complicated than the others one because there is the determinant and there is this constraint which is very hard. So we will not discuss this in the course. But this is just to say that there are many other problems in which you can naturally introduce these sparsity constraints. You can do it for the concept of principal component analysis. You have constraints on the sparsity of the principal components. You can do it in many other contexts. So this one I will skip, but so another interesting context is what is called sparse coding. Just a couple of minutes on that. So this is a different way to find representation for data points, which is very different from principal component analysis. So as we have seen, for example, in supervised learning or mathematical problem research methods, you in PCA you take a point x, right, and you try to write as a linear combination of few orthonormal vectors. Right? Here we want to find a set of vectors which are not necessarily orthonormal. It will even be linearly dependent, right, which have the property that the vectors, the input xi, which are sampled from some distribution, right, are well approximated by a sparse combination of these vectors. Right? So the vectors are the columns of the matrix W. So you say that xi is about the sum of the j, wj, zj. This is a vector, this is a vector, and these are the scalar coefficients. Okay. And here you say that many of these coefficients are 0. Right? So it's a more sophisticated approach because you have many sparse regression problems. Right? And there has been a lot of work on this, which developed the idea. And these works come from neuroscience. It was quite curious. And it was developed a long time ago, maybe in the mid-90s. I mentioned a paper. It is at the end, where they proposed this method. And they say that this works well to represent natural images. So if you sample natural images, small, you take, like small images, like 16 times 16, so they are extracted from a big landscape. And then you want to study what is a good way to represent these, also called patches, right? So they are small, you cut small patches in a big image. So you can have a tree here and sea here, or some mountain. Then you can study the statistics of all these inputs. So they are randomly extracted patches from natural images. So these people were saying that instead of doing the principal component analysis of all this, of the data, you could try to find a dictionary, so this matrix W, so a set of basis vectors, which have the property that they can be made, so they can be more than 16 times 16. Right? So in PCA, if you have 16 times 16 dimensional inputs, you will find at most 256 principal components, because they need to be orthonormal. Here they can be more, maybe they are 500, 1,000, or more. And have the property that even though there are many, when I give you a natural patch, so I started from only few of the dictionary elements will be used to represent it, right? So this is how this method works. You want to find the dictionary, which has the property that it allows for a sparse representation of the images in your word, okay, so the patches. Why it works, I don't understand, but you know, if you do the computation, you see that it seems to work well. And then there were some speculation about the brain. So that, I don't know, so you need to read the paper in Nature. So the paper in Nature, so I joke, but this is a serious paper. But at some points I think there are a bit of speculations, but which were saying that if you look at the dictionary elements, so if you look at the principal components, so the best thing is to look at the paper and see the figures, but if you look at the principal component, they are kind of all different from zero here and there. And if you take a natural image, all the principal components will be used, right? Now, if you look instead of the columns of this matrix W, which are the, not to be confused with the multitask stuff, different. These are the basis vector, which allows for sparse representation. And so they look more like localized, and they look more like the receptive fields in the brain. That's what they were saying in the paper. Right? So the principal components, since we try to code images, all the basis vectors are images, the principal component look more like this. And the dictionary elements using sparse coding, they look more like localized or something like that. So another more mathematical interpretation is that the basis vectors, right, columns of W, maybe they encode some local properties of images, maybe edges, or perhaps if you apply this to images of faces, right, perhaps parts of the face, stuff like that. And when you take a random image from your distribution, apparently natural images have the property that I think it is just tautology, that they are generated in a sparse way. Right? Now, whether this is the case or not, I don't know, but there is some speculation about that. So I think a lot of stuff is unknown, right? And, people have tried to work out the distribution, try to fit the distribution of small patches, right? And I think there is some important work by another mathematician from Brown University, I think, machine learning, and it's more from computer vision. It involves some former or current famous mathematicians. So this is another film medal, I think, but I forgot his name. So he has tried to fit the differential geometry, the distribution of natural images. His name doesn't come to my mind, but so there are some very famous works which are interesting, but they are in different direction. In neuroscience, these people have tried to describe a generative model for images, which uses sparse coding, and algorithmically, the way to find the parameter of the models, one way, is to do is to solve to solve this problem. So you try to minimize the construction error. This is the sum of the representation of each of the images. Right? So it's the sum over I, and you have xi, column I, minus w set I, same, and then you try to make each code, right? So Zi, the efficient vector, also called the codes, to make them sparse. So small L1 of which carry sparsity. So again, I spoke a lot about this. We skip clustering. But the last thing I want to tell you is to move to nonlinear models. Okay, just little. So we have discussed linear regression, the lasso, structure sparsity, multitask learning as a way of to do structure sparsity in multiple regression problems. They can be seen as a single regression problem. Then we have said that sparsity can be used also in a supervised learning. I mentioned this problem of density estimation, Gaussian graphical models, where there is a sparse graph, so the inverse covariance matrix is sparse. Then we can also use this in the context of natural images, the idea of sparse coding, which is a sparse extension of PCA. We can also use the sparsity methods for nonlinear modeling. So this is the last thing. So there is quite a bit of research activity which has extended the idea of sparsity in the context of, for example, kernel methods. There was a question during the break. How do you choose the kernel? Right? So one way to choose it is by doing this stuff. So these last slides are very condensed. But the main idea is simple. How you implement it is more complicated. So the main idea is that we don't require, say, parameter of my linear regression to be sparse, to be zero, but we required some nonlinear, some non-parametric representation of our regression function to be sparse in a more extended sense. So we require that our regression function, which is nonlinear, right? So before it was W transpose X. Right? Now I say that it is a sum of functions, say N equals to 1 to N. Now these functions are unknown, and the problem is non-parametric, because I don't give a parametric representation of my function, but I give a function representation. So I say that the regression function is a sum of functions, which are unknown, but many of them are encouraged to be zero. So the end result is that the regression function can be written as a sum of just a few functions, which are chosen in some space. So this is very the short phrase, but let's understand a little bit more how this is done, right? So we need to go back to kernels and remember what kernels are, and we go back to the group lasso. This is what we described, what I described in the beginning of the lecture. The only difference was there was not this feature map. So let me write down quickly. So we had the sum over I. Let's consider the square loss. So we had yi, then it was minus w dot xi. That's the square error. Right? And then I was saying that it was lambda, and then it was the sum over L from 1 to n, and then it was wjl, right? Which are groups of variables, right? And this was kind of structure sparsity, group sparsity, right? Only few groups are important, right? Since you use this regularizer, at the optimum, wjl is equal to 0 for most, typically, for most N. Right?
What's the set that you're summing over in the second page?
Oh, this is, no, sorry, this is from 1 to N.
Okay.
So I have my a priori known set of groups, J1, Jn, and I do this sum of the L2 norms of the restriction of W to the groups. I apply the same recipe with these nonlinear kernels. The way I do it is in the following way. So I apply. So the difficulty here is to change the notation. Believe me, the greatest difficulty is to modify a little bit the notation of the problem. And now I assume, remember with kernels, you have a feature map. And I assume I have many feature maps, right? Phi 1 to phi n. Right? So it could be that phi 1 are a linear kernel, phi 2 is polynomial of second degree, phi 3 of third degree, and so on. Or it could be other kernels. And right, then I consider as my regression function this. Right? So this is f of xi. So the linear is the sum of the function in each feature space. Right? Okay? And I require, right, rather than putting a square here, it would be like kernel ridge regression, I sum them to none. Okay. And therefore, what this achieves is